Process with the CKW4000 hydraulic press begins with positioning a preheated metal ingot or billet onto the forging plate. This press utilizes a pull-down, two-column design where the press cylinders are mounted on a stationary middle cross girder. These cylinders act downward on the lower cross beam of a movable frame, pulling the upper anvil toward the workpiece. The material is then subjected to controlled deformation through open die forging operations, such as upsetting, piercing, drawing, or ring forming. For cylindrical or ring-shaped components, the rotating upsetting table is employed. It is mounted on the press's forging plate and hydraulically driven. The table allows for rotation of the workpiece during deformation, enabling even upsetting and flattening. The spring-mounted bearing system ensures smooth rotation, while the hydraulic motor inside the table body provides power. When piercing operations are required typically to create hollow shapes, a piercing table is used. This table, also fixed to the forging plate, supports the pre-upset, semi-finished product and enables accurate alignment for subsequent piercing by the press. During the forging cycle, motion of the press frame and tools is precisely monitored by linear proximity sensors. These transmit data to a control system, allowing software-based command of the entire forging sequence. Depending on the forming force required, 1, 2, or all 3 press cylinders may be activated, especially in higher tonnage presses like the CKW4000. The press's rigid structure, long guideways, and closed-loop oil lubrication ensure high precision down to 1 mm tolerance alongside long service life. Auxiliary times are reduced through integrated systems, and energy consumption is minimized. The press can also be integrated with forging manipulators to automate handling during multi-step forging processes. The production process of copper tubes at the new facility in Malaysia begins with the milling machine, where raw copper billets are precisely machined to ensure accurate dimensions and surface quality. These billets are then transported to the planetary rolling mill, which performs multi-directional compression. This rolling process reduces the diameter of the billet and refines the microstructure, enhancing mechanical properties and preparing the material for the next stage. After rolling, the semi-finished tubes are passed into the TVO carriage drawing machine. In this stage, the tubes undergo a cold drawing process, where they are elongated and reduced in diameter by being pulled through a die. This improves dimensional accuracy, surface finish, and tensile strength. The TVO carriage system provides smooth and stable feeding, ensuring consistent wall thickness and diameter along the tube's length. The next step involves the spinner block, which further refines the tube by applying high-speed rotational forces. This improves surface uniformity and enhances tube straightness and roundness. The process also stabilizes the mechanical properties of the copper. Following spinning, the tubes are wound using the double-head winder machine. This system simultaneously coils the tubes from both ends, optimizing production time and preparing them for further processing. These coils are then fed into the straightening machine with pancake coiler, where they are carefully uncoiled, straightened to meet dimensional tolerances, and then recoiled into flat pancake shapes suitable for packaging and transportation. Finally, the tubes are processed through the IG machine, which performs comprehensive inspection and surface treatment. This includes checking for defects such as cracks, dents, or inconsistencies in shape and finish. Tubes that meet all specifications are approved for packaging. This advanced production line combines precision, efficiency, and automation, ensuring high-quality copper tubes that meet international standards. The manufacturing process at LNS North America begins with the storage of raw sheet metal in a high-density 10-table tower system, enabling efficient retrieval and material handling. Sheets are then transferred to a 6 kilowatts fiber optic laser cutting machine, where complex geometries and high-precision profiles are cut with minimal thermal distortion. After cutting, parts are manually sorted and removed for secondary forming. The components proceed to the CNC-controlled press brake, where accurate bending operations are performed to meet tight dimensional tolerances. Weldmen are assembled at ergonomic welding stations equipped for MIG and TIG welding, ensuring operator safety and precision. Post-welding, components undergo metal finish grinding to remove spatter, smooth surfaces, and prepare for coating. Mechanical assembly follows, integrating fabricated and standard components into functional systems. Painted surfaces are applied in a controlled paint booth using powder or wet coat systems. The final step involves integration of magnetic conveyors, tested for performance before shipping. Rough and finish machining of outer and inner cylindrical surfaces, conical surfaces, end faces, and slots is performed using high-speed steel tools on a double-column vertical lathe. The manufacturing process begins with wheel design, integrating performance targets and aesthetic requirements using CAD software. These designs undergo testing and 3D simulation to evaluate stress distribution, thermal expansion, and fatigue behavior under dynamic loads. Once validated, production proceeds to precision CNC machining, where forged 6061 T6 aluminum blanks are shaped using multi-axis milling centers. The machining process defines critical geometry, including hub bores, spoke profiles, bolt patterns, and backpad dimensions. Following this, surface treatment includes mechanical grinding, multi-stage polishing, and powder coating or anodizing to enhance corrosion resistance and visual quality. Quality is continually monitored through dimensional inspections and coating thickness checks. During assembly, components like valve stems, center caps, and two-piece wheel sections are manually fitted using calibrated torque wrenches to ensure uniform clamping force. Each wheel undergoes impact, radial, and cornering fatigue testing before shipment. All stages, from R&D to final inspection, are completed entirely in-house. The damaged Passat is brought to the scrapyard, where it is first inspected and stripped of any valuable or reusable parts. Then, it is moved into the hydraulic scrap press. The press crushes the car with immense force, flattening it into a compact metal block. This process significantly reduces the vehicle's volume, making transport and recycling more efficient. The compressed metal is then sent off for further recycling. A 5000 stainless steel 316 billet is uniformly heated in a furnace and placed over a rotating mandrel. A hydraulic press applies axial and radial pressure to enlarge and shape the ring. The forging continues with repeated pressing and rotation, refining grain structure. Once the required size is achieved, the forged ring is air-cooled gradually. The square pipe production process using the ITL tube mill 1/2 to 4, suitable for 100 by 100 mm section, is a continuous, highly automated method and surface quality. The process starts with material feeding, where steel coils are loaded onto the uncoiler. The strip is then fed into the line and guided toward the next station. In the leveling and straightening stage, the material passes through a leveling unit that flattens the strip and eliminates surface distortions, ensuring uniformity before forming. In the roll forming stage, the leveled strip is gradually shaped into a square profile using cold roll forming technology. The machine adopts multi-point forming, where each forming stand deforms the strip slightly, changing the contact from line touch to point touch. This reduces surface friction, enhances finish quality, and improves forming stability. The forming stands are adjusted automatically using a PLC control system. The position of rollers adapts based on the input specifications, and only one set of rollers is required to form all tube sizes. The machine's multi-motor single-drive system allows each roller stand to be driven by its own DC motor. This precise control ensures speed synchronization between stands, minimizing speed differences and preventing scratches on the surface. Next, the form tube undergoes high-frequency welding. The edges of the strip are heated and pressed together to form a continuous welded tube. After welding, the pipe enters the sizing and calibration section, where it is shaped precisely into the final square dimensions and checked against tolerance limits. In the cutting stage, a cutoff saw is used to divide the continuous pipe into required lengths. The saw operates in coordination with the line speed to ensure clean and accurate cuts. Finally, the pipes go through the finishing stage, where they are inspected for defects, then stacked and prepared for packaging. This efficient process enables consistent, high-quality square pipe production. The installation process of the hydrodynamic turbine involves placing the turbine in a suitable location, connecting it to the drive mechanism, and ensuring proper alignment with the flow of water. Once installed, the turbine begins to operate by converting water flow into mechanical energy, which is then transmitted for further use or electricity generation. Parch operates 20 production halls over 40,000 square meters, where electric machines and components are designed, manufactured, and tested. The process starts with in-house production of copper wires and laminated cores, followed by precise laser or water jet cutting. Stators and rotors are assembled with custom windings. Components undergo mechanical machining like milling, turning, and grinding. After assembly, machines such as generators, lift drives, and accelerator magnets are dynamically balanced and tested at nominal speeds. Final inspection includes electrical, mechanical, and imaging tests in the test bay to ensure performance. This is a tire shredder in action. Used car tires, including the steel rims, are fed into the shredder's rotating blades. These bond shredders are designed to tear apart rubber and metal, breaking the tire into smaller pieces for recycling. Machines like this are essential in the waste tire management industry, allowing the rubber, steel, and textile components to be separated for reuse. The pyrolysis test of the mini reactor unit demonstrated its efficiency prior to customer delivery. This compact pyrolysis system converts waste tires into valuable products such as fuel oil, combustible gas, and carbon black, which can be used for energy generation. During testing, over 4 tons of whole tires were loaded into the 18 cubic meters reactor through a large window using a special pusher. The active pyrolysis phase involves thermal decomposition in the absence of oxygen. After the cycle, carbon black and steel cord are unloaded separately. This technology offers an effective and profitable tire recycling solution. Fonderia Tironi is a leading gravity die-casting foundry that has invested heavily in advanced technologies to ensure high-quality production and workplace safety. One of the key innovations is the fully automated casting system, which is equipped with 2 human-shaped robots. This not only enhances production efficiency, but also reduces the need for human intervention in hazardous areas, ensuring a safer working environment. Additionally, the foundry utilizes computer-controlled grinding machines for precise machining of aluminum components, reducing errors and improving the overall quality of the final products. The foundry works closely with customers throughout the production process, offering internal 3D mold design monitoring. This ensures that the molds are created to meet specific technical requirements and that the final product will meet customer expectations. The production process is continuously monitored from external sources, optimizing efficiency and guaranteeing the highest quality of the end product. Quality assurance is a top priority at Fonderia Tironi, with a dedicated laboratory equipped with state-of-the-art equipment. The laboratory includes spectrometers, X-ray machines, density scales, and tensile testing machines, all of which are used to analyze the alloy's composition and mechanical properties. These tests ensure that the aluminum products meet strict quality standards and can withstand the demands of various industrial applications. This commitment to quality is reflected in a series of innovative architectures that manage human resources and business performance. Proof of this is the certification of the DNV company's quality management system, according to EN Uni ISO 9001-2008. Through this comprehensive process, Fonderia Tironi guarantees that each cast product is of the highest quality, durable, and reliable. With continuous investment in innovation, the company maintains its leadership in the competitive market, focusing on sustainable practices and its commitment to excellence in every cast, while fostering long-term partnerships with clients. The Welding Casting Degating Air Hammer is a high-performance pneumatic tool developed specifically for the efficient removal of risers, feeders, gates, and sprues in steel, ductile iron, and nodular iron castings. Designed to meet the demands of modern foundry operations, this air-powered hammer utilizes compressed air to deliver fast, controlled impact blows that detach gating components without damaging the casting itself. Traditional degating methods such as manual sledgehammers or oxyacetylene flame cutting often pose several drawbacks: inconsistent results, excessive operator fatigue, increased risk of injury, and potential damage to the casting due to uncontrolled force or thermal distortion. The WEIJING air hammer addresses these issues by providing cold mechanical impact with repeatable accuracy, ensuring cleaner separation lines, and preserving both the dimensional accuracy and surface quality of the casting. In terms of ergonomics and safety, the air hammer is equipped with vibration-dampened handles, a balanced lightweight design, and precise control valves that allow operators to perform degating tasks with minimal physical strain. This not only improves operator comfort and productivity, but also reduces the risk of musculoskeletal injuries and meets global workplace safety standards. Models such as the QC355 and QC499 deliver impact energies of 9,500 to 28,000 joules, capable of removing risers from 210 millimeters to over 350 millimeters in diameter. Despite the high energy, the tool requires only 6 bars of compressed air for efficient operation. These specifications make it suitable for both medium and heavy castings in high-throughput foundries. Features such as vibration-dampening handles, ergonomic structure, and optional remote control operation enhance precision and reduce fatigue, even during continuous use. The tool is particularly advantageous in medium and large-scale casting operations, where gating systems are often thick, dense, or difficult to remove using conventional means. Its performance has been validated in over 80 installations across the globe over the past 10 years, proving its durability, reliability, and adaptability to various foundry workflows. Additionally, the use of pneumatic power eliminates the need for high-temperature cutting, reducing energy consumption, and removing associated environmental hazards such as gas emissions, slag, and heat-affected zones. Foundries implementing the Weijing Degating Air Hammer report improved process efficiency, reduced scrap rates, and lower overall labor costs. The manufacturing of spun steel wheels begins with the roll forming of flat steel sheets into cylindrical tubes. These tubes are then welded longitudinally to close the seam and form a continuous ring structure. Following welding, both ends of the cylinder are flared or expanded to form the initial rim profile. This preformed rim is then mounted on a spinning mandrel, where high-speed rotation and external forming rollers shape the steel precisely into the final rim contour, a process that enhances material strength and uniformity through cold working. Once the rim geometry is finalized, trimming and punching operations are carried out to define bolt holes and the center bore. The wheel disc, which supports vehicle mounting, is either pressed separately and welded to the rim or integrated directly during the spinning process using specially designed tooling mandrels. Final welding ensures a strong bond between disc and rim, critical for load-bearing performance. After assembly, the wheel undergoes dimensional inspection, leak testing, and dynamic balancing. Surface treatments such as shot blasting, phosphating, and powder coating or e-coating are applied for corrosion protection and finish quality. This manufacturing approach offers a balance of strength, durability, and cost-effectiveness for commercial, passenger, and agricultural vehicles. The heavy fabrication services include handling both small and large-scale projects. The facility is equipped with overhead cranes and spacious work areas, allowing efficient movement and assembly of large components. The process involves cutting, welding, and assembling structural steel components. Advanced tools like track welders and scaffolding ensure precision. The facility also offers finishing services, including painting, to handle large projects with multiple stages, ensuring both custom and repeat items are completed efficiently. The HEPO hydraulic table is a versatile tool designed for the ornamental iron industry, built by German blacksmiths for precision and durability. It can perform a wide range of functions, including twisting, end forging, scrolling, embossing, texturing, hammering tubes, and making baskets. Additionally, it can press belly pickets and much more. The system allows fabricators to create up to 4 different belly picket profiles and make custom tooling for unique profiles. The table enables quick, cold bending of metal with minimal effort, adjusts gate arches, and fine-tunes scrolls to match templates, enhancing both production speed and creative flexibility for ornamental iron fabricators. Rolls-Royce tests jet engine components through various rigorous procedures. Vibration testing ensures blades withstand crosswind-induced turbulence. Spin testing at high-speed facilities checks balance and structural integrity. In water ingestion tests, engines are drenched to verify performance during storms. Endurance trials simulate over 1,000 ultra-long-haul flights to monitor component behavior. Noise levels are precisely measured with sensitive microphones at test cells like Stennis. Crosswind simulations assess fan blade resilience. Fatigue life testing identifies failure cycles under repeated stress. Rolls-Royce also simulates rare events like bird strikes and fan blade release to confirm containment safety. Each test ensures engines meet extreme service demands. Cut tire sidewalls, place cylinders on roadbed, fill with gravel, no compaction needed, surface optionally top. The Eco Monster is a powerful single-shaft tire shredder, equipped with a custom hydraulic power unit and a Hägglunds motor. Designed for high-throughput applications, it processes up to 12 tons of tires per hour, from semi-OTR to car tires. The system produces consistent 8" shreds, ideal for recycling or further process. The bicycle frame production process begins with the design phase, where engineers use CAD software to create precise digital models based on geometry, performance goals, and rider ergonomics. After finalizing the design, raw aluminum or steel tubes are selected and cut to specific lengths. These tubes are then bent and shaped using CNC tube bending machines. The shaped tubes are welded together in alignment jigs to form the frame. After welding, the frame undergoes heat treatment to enhance strength, followed by sandblasting or polishing to prepare the surface. It is then coated with primer and painted using automated spray systems. Logos or decals are applied, and the frames go through thorough quality check. Fusion Marine manufactures high-quality fish farming systems for salmon aquaculture using advanced plastic welding tools like the Leister Weldplast S two-hand extruder and the Triac S. These tools enable precise and durable welds in HDPE panels and components, ensuring watertight and long-lasting cage structures. The WeldPlast S2 is used for larger, high-strength seam welds, while the Triac S provides excellent control for smaller or more detailed welding tasks. This combination guarantees structural integrity essential for offshore salmon farming conditions. The SMC FMS 200 automation station at Palo Alto College is a state-of-the-art training system used to teach students practical skills in industrial automation and mechatronics. Designed as a modular and flexible system, the FMS 200 simulates a real-world manufacturing environment and allows for hands-on experience in areas such as pneumatics, sensors, PLC programming, robotics, and process control. At the heart of the automation station is a conveyor system that moves parts between various workstations. These workstations include a material feeding station, processing station, quality control, and sorting modules. Each station is equipped with sensors, actuators, and programmable logic controllers, PLCs, that communicate through industrial networks like Ethernet/IP or Profibus. Students learn how to program and troubleshoot automation sequences, integrate robotic arms for pick-and-place operations, and use HMI, human-machine interface, for monitoring and control. The system can handle multiple tasks such as detecting part orientation, assembling components, and rejecting defective items based on quality inspection. It offers real-time feedback and safety features to prevent errors and reinforce good practices. Through training on the FMS 200, students gain valuable experience with technologies that are foundational to Industry 4.0, including data collection, remote diagnostics, and system integration. This hands-on exposure prepares them for careers in automation, controls engineering, and advanced manufacturing. The automation station's realistic design and advanced capabilities make it an indispensable tool in modern technical education. Additionally, instructors can customize the training scenarios to simulate real production challenges, helping students develop critical thinking and adaptive problem-solving skills